All right, what I want to do is just run through some of the vocabulary and main ideas that you'll need to know about waves for this chapter. So here we have a list of some vocabulary words: oscillation, cycle. This could also be called a wave. It could be called a wave cycle. And so these are just different ways for us to refer to that one time through the pattern. I'll go over that more in just a second. Equilibrium is a location that we're going to refer to in various sets of examples and illustrations for our oscillating objects. A restoring force, amplitude, these are some basic vocabulary words we'll get in a minute. Electromagnetic waves and mechanical waves, these are wave categories that we're going to discuss in this chapter and the next chapter. So these are some pretty important words here. And then transverse and longitudinal, these are wave shapes, and you're going to be responsible for knowing how to identify what shape just by a drawing, and you're going to need to be able to identify the different parts of the wave on an illustration. So first we're going to talk about some basic vocabulary. So as I said, an oscillation is the same thing as a wave cycle, a cycle. And so this is just one full time through the pattern. One full time through the pattern. So what we have are particles that are being oscillated. In many of our examples today, we're going to talk about oscillating particles. And so whatever our object is, whatever our thing is that is oscillating, we have this pattern that they're going to go through, where they're going to go back and forth, up and down, right, left, whatever that may physically look like. But it's just going to repeat that pattern, back, forth, back, forth, back, forth. And so instead of getting caught up or mesmerized in that repeated motion, we just say that one time through that motion would be just one oscillation or one wave or one cycle. Okay, so that's a word you're going to be reading and hearing quite a bit. Equilibrium is a term that we have used in previous chapters. So this is going to be a statement where we have balanced forces, and this is something that we've talked about in this class before. So here it's defined as the neutral or resting position. This is a location where we have a net force of 0. So if we look at these illustrations that I have here, imagine somebody on a swing. If we allow them to rest, there is our equilibrium or resting position. If these particles here are oscillating up, down, up, down, up, down, then our neutral or equilibrium position would be somewhere right along here, because that's going to be their neutral or resting point. That's what we mean by equilibrium. The restoring force is a force that is always going to be back towards equilibrium. This is a conceptual thing that I just need you to understand. If those particles have been moved out of that neutral or resting position, number one, there was a force to cause it to move, but number two, in order for it to come back, there's a force acting on it, sending it back towards equilibrium. Amplitude is a vocabulary word that we're going to need to comprehend in order to interpret lots of pictures. So amplitude is defined as a maximum displacement from equilibrium. So a few things to point out here. Displacement from equilibrium, we're measuring how far. This is going to be a linear measurement, and so it is going to be measured in meters. But it's not just at any location along the pattern. It has to be specifically to the point that the particles will get the farthest away. So we've got to make it that maximum displacement. For our waves in general, super important. Up here at the very, very top of the screen, waves carry energy. That is a quiz test question all day long that I need you to know the answer to. Waves carry energy. That is the main idea behind the waves that we'll be covering for the next two chapters. Now it says here that it carries energy through both matter and space, and so you'll see the difference in these definitions. So let's get right to it. Mechanical waves are waves that are going to require a medium. So when we talk about mechanical waves, this is what we're focusing on in this chapter. We are focusing on waves that are going to need to have some sort of particles, a medium is a material. This means that we have atoms, we have matter. So waves that require atoms in order to allow that energy to be transferred. That is our mechanical wave. And so we will be focusing on mechanical waves in this chapter. So we're going to come back and we're going to talk about sound in a couple of more lessons, specifically because sound waves happen because atoms are being vibrated or oscillated. Electromagnetic waves are different because these waves do not require a medium. So when we say no medium needed, that means that if we were to remove all of the molecules, if we were in outer space, if we were in a vacuum, right, no particles. You see our example here, light. We could still have light even though there are no particles, because although light is a wave, it does not require those atoms in order to carry the energy. So our examples here are light and radio waves, and we'll talk about those more specifically when we get into the chapter focusing on electromagnetic waves. In this chapter, we're going to be focusing on mechanical waves, so our waves are going to require some sort of material. Now, for our wave shape, waves carry energy. So the way that this energy is going to move will be a couple of different shape options for us. The first wave shape is called a transverse wave. And so transverse waves are identified here as waves that oscillate perpendicular to the direction of the energy. So we're going to go ahead and bounce to an example right now. So transverse waves oscillate perpendicular to the direction of the energy. So if I'm trying to shorten that definition, that's what I would write. So here I have an illustration of a transverse wave. Here we have a different explanation. Matter in the medium oscillates back and forth. So when we say that the matter moves back and forth, if my particles are simply vibrating or oscillating, bouncing up and down, up and down, up and down, this molecule doesn't actually leave this location. It's just going to go back and forth from these two positions. So that's what we mean when we say oscillates. Now, it says here at right angles to the direction of the wave. If this were an animation instead of a photo, instead of a picture, what we would see is that as these little red and blue squares oscillate up and down, we would get this wave pattern that kind of moves across the screen left to right. This is what we would be seeing with our eyes. And so there we would say that the energy itself is moving across the screen to the right. So if we say that our particles are oscillating vertically up and down, and the energy is traveling horizontally, in this case to the right, well, these two lines make a right angle, or they are what we would define as perpendicular to each other. So now we should have a better understanding of what it means to say that transverse waves have the particles oscillate perpendicular to the energy. You will need to know the different parts of a transverse wave, so let's do that right now. The top of the wave is called the crest. So the crest of my wave is going to be the highest point, the maximum positive position. That's going to be our crest. The trough is going to be the lowest part of the wave. And so here at the very, very bottom, this lowest part, these valleys, whatever you want to call it, that is our trough. And so these are just locations. Then we have our amplitude. And our amplitude, once again, is going to be a maximum displacement. So we have to measure from this highest point up to that equilibrium or neutral line, which is drawn for us in this picture. So amplitude cannot be measured here because that is not a maximum position. Amplitude can be measured on either the positive or the negative side. It doesn't really matter as long as we measure it from that equilibrium point to the greatest displacement. And then here on the screen, we have a new vocabulary word called wavelength. And so wavelength is exactly what it sounds like. It is a length that's a how far for one complete wave cycle. So in this picture, if we start tracking our wave at this location, we have to allow it to go through both the positive and negative, the up and the down, the crest and the trough phase. And then after it has gone one complete time through the pattern, that's the end of the wave. And so we're going to stop our measurement. So notice that it's one wave and it is a linear how far. So from here to there, how far, and so this is going to be measured in meters, and so that's how we would mark or measure our wavelength, okay? And so this is a transverse wave. Now the other type of wave shape was called a longitudinal wave, and so here we identify a longitudinal wave as being a wave that oscillates parallel to the energy of the wave. So let's take a look at a longitudinal wave and see how that is going to be different. Our longitudinal wave is sometimes also called a compression wave, but if we look at our wave down here, we have an area where the molecules are squished or packed in together, and so this is going to be one of the phases, one of the parts of our wave. The alternate part of the wave you can see is spread out. So here we have our molecules that are much farther apart. And so this is the relaxed or spread out part of the wave. And so that we are going to call rarefaction. It comes from a Latin root, I believe, that means to be spread thin. So my two parts, instead of a crest and a trough, they're going to be a compression and a rarefaction. Now we can still measure our wavelength here. Again, it does not matter where you begin your measurement. You simply have to allow your wave to complete the pattern, and then that would be the end of your wave. And so once again, it's a linear how far to give us our wavelength. If we decided to start measuring our wavelength here, we would need to get to the middle of the next rarefaction, and that would be the end of our wavelength, okay? So longitudinal waves, the matter is going to oscillate parallel to the wave. So what this means is that these molecules are now going to be vibrating right-left. They're going to be bouncing back and forth to the right and to the left. And so the particle motion is going to be right-left. If we were to see this as an animation, what we would see is that we have all of these particles spread out, and then as our force comes and compresses the molecules here, those molecules are going to pass and bump into the other molecules, causing them to also be compressed. And then those molecules are going to pass the energy, causing another set of molecules to be compressed. And so what we end up having is this movement of energy, which is going to be horizontal in this case. So the energy is horizontal, the particles are horizontal, and so since they are both happening along the same axis, we call those parallel lines, and so that's why it's identified as being parallel. All right, our longitudinal waves and our transverse waves are going to be illustrated in a variety of ways. So here is just a different example. We might see our longitudinal wave shown as just a whole bunch of dots to represent some of our molecules. So just be familiar with recognizing the wave shape and being able to identify those parts. All right, now we need to talk about a couple of vocabulary words. Here we have the vocabulary word period, and so let's take a moment to focus in on what this word means. This is an amount of time. So you see here our symbol, which we're going to use in our math formulas, is a T for time, but notice it's a capital T. So what we've done in the past is a lowercase t for time, and this could be a lowercase t, except that we have a very specific thing that we are monitoring in order to trigger our timer. So remember that we are talking about things that are repeating a pattern. So my particles are oscillating back and forth, back and forth, back and forth, back and forth, and it just keeps on going in that pattern. And so what we did, or what we would do if we just kind of started the timer like, let's just watch it oscillate, and when it's done, I'll stop the timer, that timer is going to go on forever. So instead, we are very specific. So this is why we don't call it a T for time. We call it a period. It's a capital T for period. So this is specifically the amount of time that it takes, but for only one oscillation. So my particle might vibrate up and down, left and right, whatever, 1,000 times. I'm not interested in how many seconds it takes for it to oscillate 1,000 times. I'm interested in how many seconds it takes for it to oscillate one time. So we're very specific in this definition. Here we have a graph where they are showing me my particle's position. So this is not a picture of a wave. This is a graph. So we are showing that my particle is at equilibrium. Anytime we are here, it's at its neutral point. And then here we are 5 meters away. Doesn't matter if it's right, left, up, down. 5 meters away on the positive side. And then here we would be 5 meters away on the negative side. So this is just a graph. Okay, just a graph, not a picture. So from this graph, if I wanted to know what the period of my wave is, pick any position on the graph, start the wave, let it complete the wave cycle. And so what we're going to do is we're going to say, okay, there was one wave. Now you can see this graph has time on the x-axis. So if that is one wave, I'm simply going to say how much time from this point to that point. It was 10 seconds a time, so this wave has a period of 10 seconds. Now, the other word on this screen is frequency. Frequency is inversely related to period. So let's talk about what frequency is. This is defined as the number of times it takes a wave to oscillate in 1 second. So how many oscillations when it says each second, that means only 1 second of time. So when we're talking about frequency, this is a lowercase f as a variable, not as a subscript. So please don't get confused. A lowercase f for frequency. And so this is going to tell me how many waves per second. So this is the number of waves or the number of cycles for every 1 second of time. So when we go to calculate the frequency, we end up with some number over the number 1. Seconds is in the denominator, and then we don't have a unit for the numerator because a wave is not a unit of measurement. A cycle is not a unit of measurement. An oscillation is not a unit of measurement. It is an occurrence of an event, not a unit of measurement. So when I look at my units here, I end up with seconds in the denominator. It would be an implied 1 in the numerator, so I end up with 1 over seconds. Well, for this particular variable, we're not going to choose to express it as 1 over seconds. Instead, we are going to say 1 over seconds is equivalent to something that we're going to call a hertz. So frequency is a variable measured in hertz. It tells me how many oscillations per second. So if we look at the examples here, if we pretend that each of these graphs gives me 1 second of time along the x-axis, they are showing us visually that my frequency has increased because you can see I have fit more waves inside of that 1 second. If we are going based off of the definition, it's the number of waves per second. So here is 1 complete wave cycle. So 1 wave per second, that's a frequency of 1. Here is 1 complete wave cycle, but remember I'm not counting just 1 wave, I'm counting how many waves in 1 second. So here would be the next wave cycle. Here would be the next wave cycle. And so this picture gave me 3 waves in that 1 second of time. So it would be a frequency of 3 hertz. All right. Main idea on this slide is right up here at the top. It says frequency and wavelength are inversely related. This is a very important relationship that you need to know. I would suggest you write it down. It will come across several different questions for you. And so what we're trying to simply get you to understand is that if we look at these pictures, my wavelength has been marked for me. You see how my wavelengths are getting shorter and shorter? But let's look at my frequency. My frequencies are getting larger and larger. So as my wavelength decreases, my frequency increase. They are inversely related. So the shorter the waves are, the more waves I can fit in, right? In that 1 second at a time, that kind of is common sense. So however you want to think about it, make sure you know that relationship. It asks here, does amplitude affect the wavelength or the frequency? The answer is no. That's a trivia question you're going to want to know. Amplitude does not affect frequency or wavelength. And then the last main idea down here, period and frequency are inversely related. So we're supposed to know that the amount of time that it takes is going to decrease as the frequency increases. Why? Because those waves are going to occur much more often, which means each wave must take less time than before. So here we have some equations. Frequency is 1 over t. So for my math brain people, here's how you can know period and frequency are inversely related. And then we have down here at the bottom, V is equal to F lambda. Let's just go over that really quickly. This is my V for speed or velocity, and so that's going to be in meters per second. Then I have frequency measured in hertz. Wavelength, remember, is a new variable for us. This is pronounced lambda, and this is in meters. I'm sorry, not meters per second. This is in meters. And so if we were to do the algebra here, I would have hertz, which is the same thing as 1 over seconds, times meters, which is going to give me meters per second. So there, for those of you who like to understand how the units play out, that's how that works. All right, the last thing that we need to address is this slide here with some fun facts. You'll need some of this information in order to be able to complete some of those practice assignments that you're going to receive. So it says here, the average speed of sound when traveling through air is 340 meters per second. So this is the velocity that you're going to use for a sound wave. And a couple of questions that you're going to get, they're going to talk about a sound that's traveling and you need the velocity. So use this number. We are going to have 2 days at least just talking about sound. And so I'll come back and readdress both of these fun facts at that time. The second fun fact says that velocity is constant when traveling through a particular medium. So if you have a wave that is traveling in water, and this wave has a velocity of 322 meters per second. And then the story says that you have a second wave traveling in the same water. It is going to be automatic that the second wave is also going to have a velocity of 322 meters per second. That's what we mean by this fun fact. The velocity is constant through a particular medium. Remember, medium means particle, matter, material, things like that.